Before we go back to our servos and our robot, we need to get just a little bit more sophisticated with the blinking of the light on our PSOC. If we do this now, it will make setting the positions of our servos easier later. In this video, we're going to make the LED light on the PSOC blink at different rates. And we're going to do this by using a function called pulse width modulation. Pulse width modulation, which is abbreviated as PWM, allows us to use one of the output pins on our PSOC to produce a regular string of high and low pulses. These high and low pulses will occur at a specified interval. Whenever the pulse of voltage on the pin goes high, the light will go on. And whenever the pulse goes low, the light will turn off. Let's write some PWM code to turn the light on and off, and that will help to explain how PWM works. First, go back to the top design page of your PSOC code. Now, inside the digital menu, expand the functions submenu and find the item called PWM TCPWM mode. Click and drag one of these to the screen. This PWM block has one input called clock, and it has a number of outputs. For now, the only output that we care about is the one called line. This output is the one that produces the string of pulses of voltage that the PWM will produce. We want this string of pulses to go through our pin 1, which is our LED. So, click on the logic low that we placed earlier and hit delete to remove it. Now we want to connect pin 1 to line. So click on the wire tool, move your cursor onto the line output and then click. Then move your cursor until it connects with the wire going to pin 1. When your cursor changes into an X, click again. Now our pin 1 is connected to the line output of the PWM. We now need to connect something to the clock input. Since a PWM produces a string of voltage pulses, we need to have a clock to use as a timer to determine when the pulse will turn on and when the pulse will turn off. We can get a clock from our menu on the right. Scroll all the way down until you see the menu item called System. Expand System and then scroll down again until you see the item called Clock. Click and drag a clock onto the screen. Then use the wire tool to connect this clock to the clock input of the PWM. Now our PWM function is all set up in the top design, but we still need to set some of the settings. Double click on the PWM block to open up its settings. You will see in the Configuration tab that PWM is already selected. We're going to leave that as it is and click on the PWM tab. Here there are many different settings that we can set, but there are 3 settings that are particularly important for us. One is the Prescaler, the next is the period, and the third is this compare item. These 3 settings are the 3 that we will be concerned with in order to produce our string of pulses. To help you understand what each of these 3 settings does, I'm going to expand this settings window. Down here we see a diagram that's labeled line. Remember that line was the output that we connected to our pin. This diagram is showing what will happen with the voltage being put out this pin. The voltage will be low, that is off, then it will turn on, stay on for some time, turn off, stay off for a very short amount of time, then go on again, stay on, turn off, stay off for a short time, turn on, and then stay on for a while, and so forth. This string of pulses will repeat continuously. We can change aspects of this pulse string by adjusting the numbers in the prescaler, the period, and the compare value. Let me show you what will happen with this pulse string when we change some of these numbers. First, let's try and change the compare value. The compare value determines how long the pulse will stay on. Let's suppose that I change the compare value to approximately half of what it is right now. So right now it's set to 65,535. I'm going to reduce it to 30,000. You'll notice that the pulse string here has changed. The pulse string is now on for about half as long as it was on before. That's because the compare value determines how long the pulse string is on. So if the compare value determines how long the pulse is on, what is it that determines how long the pulse is off? That is somewhat determined by the period value. The period value determines how much time passes between the turning on of the pulse and the next time the pulse turns on. The amount of time between here and here is determined by the period. That is why our pulse string appears right now as if it is on for half the time and off for half the time. That is because the period is roughly twice the size of the compare value. If we wanted the pulse to be on for 3/4 of the total amount of time, I could make that happen by changing the period to 40,000. Since the period value is 40,000 and the compare value is 30,000, the pulse is on for about 3/4 of the time and off for about 1/4 of the time. So now we can see how the period and compare values are related to each other relative to this pulse string. But we haven't yet seen how to figure out how much actual time the pulse is on versus off. We've only seen how to change the comparative amount of time that the pulse is on versus off. Suppose that we want the pulse to be on for exactly half a second, and we want the pulse to be off for exactly half a second. We would know that the period value has to be twice as much as the compare value, but exactly what numbers should we set here? The way we figure that out has to do with the prescaler, and it also has to do with the speed of our clock. If we look back at the clock that we placed on the screen, we can see that in little numbers underneath the clock it says 12, and then it has this symbol MHZ. MHZ stands for megahertz. 12 megahertz means that this clock ticks 12 million times every second. The number that we put as the compare value tells us how many ticks of the clock will elapse while the pulse is on. In other words, if we would enter the number 12 million for the compare value, the pulse would be on for 1 second because our clock is ticking 12 million times every second. If we would enter the number 6 million for the compare value, then our pulse would be on for half a second because 6 million is half of the 12 million times that the clock ticks every second. Unfortunately, we cannot write the number 6 million for the compare value. The maximum number that can be written for either the compare value or the period value is 65,535. If we want the LED to stay on for half a second and then off for half a second, we need to make our clock tick slower than it is currently ticking. That's what the prescaler number is for. Right now, the prescaler is set to 1x. That means that the clock will tick at 1 times its current speed. The clock will tick at 12 million times per second. We can slow the clock down by choosing a different prescaler. For example, if I would set the prescaler to 2x, then that means that the clock will tick at half its current speed, or 6 million times per second. Or, suppose that I select a prescaler of 4x. In this case, the clock will tick at 1/4 its maximum speed, or 3 million times per second. Let's do a little bit of math to figure out what the compare and period values should be with what prescaler in order to achieve our goal of having the LED blink on and off at intervals. We can figure this out by doing a simple unit conversion. Here's how we'll write the equation to figure this out. On the left, I'm going to write what I'm looking for, the compare time, in units of number of ticks. That will be equal to the clock speed, which is in units of number of ticks per second, times the compare time in units of seconds. Now, since the prescaler has the effect of slowing down the clock speed, here's where we put the prescaler in this equation. We will divide the clock speed by the prescaler. Similarly, we can write an equation for the period time. The period time in units of ticks is also equal to the clock speed divided by the prescaler times the period time. If we want our LED light to flash on and off 10 times every second, that means that we want our period to be 0.1 second, and we want the compare time, the time that the light is on, to be half of that, or 0.05 second. Let's figure out what the period is first. We plug in the value 0.1 for the period time. We don't know what the period time in ticks is yet, and we also don't know what the prescaler is. But we only have a limited number of options for the prescaler, and we know that the period time in ticks has to be less than 65,535. So let's start with the prescaler of 1 and see what value we come up with. 12 million divided by 1 is 12 million. When we multiply that by 0.1, we get a period time of 1,200,000. That's bigger than 65,535, so a prescaler of 1x won't work. Next, let's try a prescaler of 2x. 12 million divided by 2 is 6 million. Multiplied by 0.1 gives us 600,000. That's still bigger than 65,535. So a prescaler of 2 won't work either. Next, let's try a prescaler of 4. 12 million divided by 4 is 3 million. Multiplied by 0.1 gives us 300,000. That's still too big. Next, we try a prescaler of 8. 12 million divided by 8 is 1,500,000. Multiplied by 0.1 gives us 150,000. That's still too big, but we're at least starting to get close. Next, let's try a prescaler of 16x. 12 million divided by 16 is 750,000. Multiplied by 0.1 gives us 75,000. That's still too big, but now we're very close. Let's move on and try 32x next. 12 million divided by 32 is 375,000. When we multiply that by 0.1, we get 37,500. That's smaller than 65,535. So it looks like 32x will work. Let's fill in these numbers in our PWM settings. I'll set the prescaler to 32x, and I'll fill in a period value of 37,500. That will give us a period time of 0.1 second. Now, if we want the LED to be on for half that time, that means we want the compare time to be 0.05 seconds. So I'll fill in the same prescaler, 32x, and I'll fill in the compare time of 0.05 seconds over here, and I'll compute this equation. 12 million divided by 32 is 375,000. Multiplied by 0.05 gives us 18,750. So I'm going to fill that in for the compare value. When we look at the pulse shown in line, we see that it does appear to be on for half the time and off for half the time. And we've set the period value so that the amount of time between one pulse going on and the next pulse going on will be 0.1 second. So our LED should flash 10 times a second. Now let's go back and finish up our code so that we can test this and see if it works. Let's click OK. Now, go to the main code. I'm going to delete this code that we already have for flashing the LED because we're going to substitute it with new code to use the PWM to turn the LED on and off. The first thing we need to do here is to start the PWM. I'm going to write this line inside of the main function, but not inside of the for loop, because I want the PWM to start only once. Once we've written this line of code in, we can go ahead and build our code to check to see if there are any errors. If your build succeeded, next we need to program the PSOC. Once we get this message that says the device was successfully programmed, you should see the LED on the PSOC flashing quickly at 10 times per second. Now I want to note that if we wanted to, we can change the settings of the PWM in our code. In fact, we're going to want to do that once we get to setting the servo angles. So let's take a moment now to see how we can do that. Let's suppose that we want the LED to alternate flashing quickly and flashing slowly. In the for loop, let's start by setting the period to the value that we already have, which is 37,500. And let's set the compare value to what we already have also. The functions writePeriod and writeCompare allow us to set the period value and the compare value in our code. The compare value that we had was 18,750. Let's allow the LED to blink at this rate for 2 seconds. So we'll use our cy delay command to pause at this point in the code. Now let's change the period and compare values to make the LED flash at a different rate. Let's suppose that we want the LED to flash faster. In order to do that, I'm going to divide the period value in half. And I'm also going to divide the compare value in half. This should make the LED flash twice as fast as before. Let's allow the LED to flash for 2 seconds here also. Now let's build the code to check for errors. Then let's program the PSOC. You should see your LED alternate between slower and faster flashing every 2 seconds. Now, LED flashing by PWM can sometimes be a useful skill, but as it turns out, PWM is what we use to set the speed of motors also, and it's also what we use to set the positions of servos. So PWM is a very useful skill in robotics. In the next video, we're going to see how we can use these same PWM coding skills to make our servos for our robot move around.